This is 3.4 Ideal Gas Law. Our outcome is I can explain the relationship between macroscopic properties of a gas or a mixture of gases using the ideal gas law. So the ideal gas law relates several variables that affect gases into one expression. So PV equals nRT. P is pressure, V is volume, N is moles, R is the gas law constant. This has many possible values. The correct R value is selected by matching the units that you need to cancel out. And then there's T, which is temperature. So these gas law constant values, these are not equations. They are just a number with units, and we need those units to cancel out. So there's actually hundreds of gas law constants, all with different units. These three are kind of the most commonly used ones in chemistry. We also have Dalton's law of partial pressures. Basically, the total pressure of a mixture of gases is just equal to the sum of the partial pressures of the gases. That means that if we multiply the total pressure by the mole fraction of a gas, we can get the pressure of the individual gas. So in question 1 here, we have 33 grams of potassium bicarbonate being decomposed at 520 degrees Celsius and 800 millimeters of mercury. So first we want to figure out how many moles of each gas is going to be created. So I'm just going to use stoichiometry here. I'm going to convert 33 grams of my potassium bicarbonate into moles, and then I'm going to use a mole ratio to get moles of carbon dioxide. Now, since carbon dioxide and hydrogen have a 1-to-1 ratio, we have 0.16 moles of water vapor as well. So what volume are they going to occupy? So in the ideal gas equation here, we are looking for V. So my pressure was 180 millimeters of mercury. This means that I want to make sure I choose the correct R value that has those units in it. I'm looking for volume. I know the total number of moles from adding together my moles of each gas. And don't forget, in the R constant, you're given Kelvin as your unit of temperature. So we need to make sure that we convert our temperature into Kelvin. So I just rearranged by dividing by P, plugged everybody in, and then my answer is 18 liters. So again, with that R constant, we're trying to make sure that the units are going to cancel out there. So the partial pressure of each gas, so I can take the total pressure times the mole fraction of the gas. So half of my gas is carbon dioxide, so half of the pressure is coming from carbon dioxide. So carbon dioxide is going to be a pressure of 440 millimeters of mercury, and the water vapor will be also 440 millimeters of mercury. So what mass of KClO3 do I need to produce 29.5 liters of oxygen at 127 degrees Celsius and 760 millimeters of mercury? So in this case, I'm solving for moles here, and then once I know moles, I can work backwards to solve for the mass of KClO3. So in order for me to produce oxygen that has these variables, right? This pressure, this volume at this temperature, I need a certain number of moles of gas to accomplish that. So I just rearranged my equation and solved for moles of oxygen here. Then, now I need to figure out how much of this KClO3 do I need to produce this amount of oxygen. So I took my moles of oxygen and used a mole ratio to convert to moles of potassium chlorate. And then I just used its molar mass to convert to grams. So our reflection question, gases behave most ideally when there are no intermolecular forces. So what conditions are going to minimize those attractive forces? So we want high temperature so the particles are moving very fast and can't interact with each other. We want low pressure So again, there's fewer collisions and interactions. And we're going to want a big volume so they have lots of space to be in and not be attracted to each other.